Alright, here goes your video for Unit 5, Target D, which is about volume, and this is the last target of the year. Probably this will be more funny at the end if you don't get it yet. Alright, so as we saw in class, the solids of revolution happen when you rotate a given function around, in this case, the x-axis. Hopefully you can see that all the cross-sections that are formed will be circles. You can see if you were to slice the shape at any given point, there would be a circle, and the radius of the circle would just be equal to the y value. So that's an important thing to know, that the radius is the y value, or the height, or just f of x, because that's the same thing as y. So if you think about the area of a circle, hopefully you remember that is pi r squared. So now, if you think about adding up all the circles, the sum of all the circles, which are the slices, that's why we need the integral. So we're going to keep the volume is equal to pi r squared, except we're not really going to write r, right? We're just going to write pi, what did we say r was? Well, that is f of x, and that is squared, and that is dx, which again, dx is right here. It's like the width or the change in x of your circle. So that's basically how you find the volume using what we call the disk method here. So make sure you have that formula, and then we'll put that into practice. So area of a circle, pi r squared, with the integral, oh sorry, I need the bounds. In this case, a and b are the bounds because we don't have any given numbers, but we will have numbers when we do our examples right here. Alright, so our function is 2 sine of x, which would be this right here. It's being revolved around the x-axis, so you would spin this way. That's why we have all of these circles. So the radius, again, is just whatever the height is, which is, 2 sine of x, because that's the f of x value. Okay, and our bounds, it looks like we're going now from 0 to pi over 2. So as I set up my volume, again we've got pi r squared, well 2 sine of x squared, again dx for the integral. Now check the bounds, we just said from 0 to pi over 2. So the only fun thing always to remember is that you always have an equation for r. Sometimes people forget that, so that's very important that you have an equation right there, and of course we're going to say squared because that is like r squared, pi r squared. Now you would just go ahead and plug all of that into your calculator, and I'm not even going to do that now just to save some time, but your calculator can get you an answer, and that's what would be expected on the AP exam. Alright, let's see what you can do on your own. Alright, well hopefully you were able to see the bounds were from 0 to 2, as we put those right there, and that you were able to see the radius is the same as the function, or the equation, which is x to the 4th. As you can see, the circles are changing size, but the radius always will be reflected by this equation right here, x to the 4th. So, the equation here that is circled for volume is the correct integral. Of course, you could simplify this right here with exponent rules, but that won't always be so easy to simplify, so you don't really have to simplify that right now any further. Alright, so we're still talking about solids. Alright, so you see two similar things, but there's something that's different between each of these. What do you see? Well, hopefully you see that we still are talking about circles as our cross-section, so we're still talking about disks that are made up of circles as we're going. But what's different about these cross-sections is actually that you are revolving this first one around the x-axis, and the second one is actually being revolved, whatever this function is right here, is being revolved around the y-axis. So very similar things. You still are thinking about pi r squared for both of these. However, in this case we have always used a function, squared times dx, and the function had the x variable. And now, sorry about that, and now we're talking about a function here where we're going to use a function with y as the variable. So that's probably how I would write this. You can see this image. Thank you, Google. Had a slightly different thing, but essentially now you're going to need to use y as your variable because you're spinning around the y-axis. Everything here is c and d. Those are y values here. So hopefully that makes sense. We'll try an example right here. But make sure you have this formula written down for when we're going about the y-axis. And we're still looking for volume. Alright, here we go. So our function is y equals x to the third, and our bounds are y equals 1 and y equals 3. Well, that makes sense because, again, we're going around the y-axis. So here's a fairly helpful picture. Y equals x to the third, which would continue over here, but we don't really need that part of the graph. So we're just going from y equals 1 up to y equals 3. So you can also see the 3D version over here. Looks like a solid figure. So again, we've got volume equals pi from some bound a to b, and then we have our, in this case, f of y dy, because we're talking about the y-axis, and sorry, that should be squared there. So, okay, we've got our pi. We've got our bounds from 1 to 3. We've got something squared and then dy. Now, do we put x to the third squared? Is r equal to x to the third? No. Why not? Well, we're spinning around the y-axis. So now we actually would need to have a function with y in terms of the variable. So actually, we're going to actually go ahead and take the cubed root, and that is what function you have graphed here if you imagine flipping in terms of y. This is the cubed root of some x value. This is the cubed root of some x value. So essentially, we do not want that. We would rather write pi. These are y values again. This is a y value, and then dy. Again, don't forget squared, pi r squared. So that is what you'd want to punch into your calculator to get the volume of this solid of revolution. Just make sure you have y values all the time, and even your equation. Alright, your turn. This is around the y-axis, so be careful that you are going this way. Thinking about this revolving, that was kind of cool, zooming in, revolving around this way, so you might have something that looks like that on the other side, and all of your circles are going that way. Kind of a rough picture there for you. So, what is the volume? Alright, hopefully you were able to get pi. Looks like our bounds for y are from 0 to 2. And our function, we wanted to use the one here that was in terms of y, so the y squared dy, but again, you still have to do squared because that's pi r squared. And r is just the y squared function. This is y squared, which makes sense if you think about it. Y equals 2, 2 squared is 4, y equals 1, 1 squared is 1, so that's the right equation, and this whole area is rotated around on this side now. So that is your integral that would give you the volume. Alright, one last type of volume that we saw in the videos in class. We saw what we call the volume by washers. Well, remember, washers are those little tools that are completely flat and they have a hole in the middle, and then there's something around the outside, a circle. So that's a washer. Why is that an example? Well, you can probably see that we have a hole. In any case, here the hole is pretty big, and here the hole is a little bit smaller. So let's just think for a second, because we're still going to be thinking about circles. So if we thought about this whole circle right here, the large circle, with, let's just say, capital R, we would say that the area is pi r squared, right? And then if we were going to focus on this inside ring, which is hollow, we'd have a smaller r. So that would be maybe with a lowercase r. And to find the total, you just want to take the pi capital R squared minus the smaller r squared. So that's basically subtracting this space that is empty. Okay, so that is what we're going to use now as we do our volume equation. We're going to have pi, still some bounds, with capital R squared minus lower r squared. And then that's still in terms of x right now, because these are all functions in terms of x. So in this first case, we would have the capital R being, sorry, that's not a good idea. If they're spinning around the whole x-axis, the capital R is this, because that's your whole big outside circle, which again is just given by the equation, square root of x, capital R. But then you have, it looks like the function 1/2. Which you can see going across this line right here, the 1/2 function. So inside of here, this orange cylinder is the whole. So that's the part that you're going to be subtracting with your lowercase r squared. And your lowercase r is 1/2. So this example would be pi from, maybe that's x equals 1/4 up to x equals 4 bounds of the larger r squared minus the little r squared dx. And that's how you get the volume. Alright, one more example. This is one we had in the video. So again, you should be able to see that there will be a small r, which is the whole, and then there will be a larger r, given by, actually, again, square root of x. This function right here appears to be 1/10 of x. That's our function. And we'll be spinning around down here, so there will still be a hole, but then you will have a bunch of solid reflected down here as it rotates all the way around. Okay, so volume is some type of pi r squared, but now we're going to subtract out the empty part. We have some bounds. It looks like in this case our bounds are from 0 up to, that's probably what this is telling us, x equals 4. The capital R is square root of x. And the lowercase r is the lower function, the lower bound, which is that. And that's actually all you need. Alright, I hope this is making sense. Here's one for you to try. Make sure you're going around the x-axis, so you're going around this way here. Make sure you have your little r and your capital R and your lower bound and your upper bound. Alright, hopefully you saw the little r, which is where the hole is x squared. And then therefore the bigger r would be just x. Lower bound 0, upper bound 1, so we have the volume is pi from 0 to 1 of x squared minus x squared squared, and that is with dx. Alright, last time, here's a challenge question. We're going to take the same shape, but we're going to rotate it around the y-axis, going this way. So, same thing, r, and lower, and upper bounds. Whoops, sorry. Alright, well, that was a good challenge, and hopefully you could see that the small radius is the function here on the inside, the linear function, y equals x. And the small radius is the larger or upper function, which is this one. However, you needed to get that in terms of y, so it took the square root to get square root of y. Bounds are still the same, just because the y values also go from 0 to 1. So our integral is pi from 0 to 1 of the square root of y squared minus y squared dy. y. All right, nice job. I know that was a long video, but it was our last target. So please write that down and then make sure you let me know if you have any questions. And maybe now you see why this is called revolutionary, since we've been talking a lot about the solids of revolution today, specifically using these methods. So what questions do you have?